wanted to get this recorded for Ava. All right, so mole fraction, we just think about that terminology. We would look at, and this of course is if we have a combination of gases. How many moles of that gas do we have? I'm just going to refer to it as one compared to total moles. So in our air, we could look at the mole fraction of nitrogen divided by the mole fraction of total nitrogen plus oxygen plus carbon dioxide, and on and on and on. We give this a special symbol. Don't know, what do we call that in Greek? I'm not sure. Is it chi? Thank you very much. Fun letter to write. So it would be the mole fraction in terms of that gas. However, if we have a multitude of gases, you could also express the mole fraction of a second gas. It would just be moles of the second gas over total moles. So that'll be handy in this unit and future units to just remember. That'll come in handy. Okay, next. In your handy dandy little colored packet, would you mind turning to page 2? Bottom left reveals page number. Not expecting us to remember. I think definitely in my teacher perspective, with first-year chem students, when we're studying gases, 2 of my favorite labs definitely are where we produce and then collect oxygen in multiple vessels, produce and collect hydrogen in multiple vessels. And then we test it different ways. The hydrogen, really fun because you bring a flame to a flammable gas and you get big flames out of your containers. Not sure if we remember that. If I was lucky to teach you, then in first year chem, we use green bins and would fill them with water. I'm not sure. Does Mrs. Kendrick use nice little white containers? Yeah. But you fill that with water and then you fill the vessels with water and then you have a gas generator that then displaces the water. Well, what we have here is just a little modification. This would be our gas generator. So whatever is going on here, if it is producing a gas and we want to collect it. If we can just think about this, if we just had even an overturned beaker and we are tubing in gas, is it the pure gas? There's going to be diffusion. We're going to lose some of that gas. Other gases are coming in. But if we collect it over a liquid, and water's just easiest, plentiful, cheap, safe, then if it starts filled with water, this gas should be what's produced from that reaction. Yes? But there's a little curveball when we collect over water. That is what we're going to collect a gas over. Again, plentiful, safe for us, cheap compared to other liquids. Wherever there is liquid water, there is water vapor. Wherever there is liquid water, there is water vapor. Wherever there is liquid water, there's water vapor. Even though water molecules are wonderfully attracted with hydrogen bonding, through their movement, some are going to get enough energy to overcome that particle attraction. So in here, you don't just have your gas. So maybe we are performing decomposition of calcium carbonate. We'll get calcium oxide left in this test tube, and then we'll produce, and we want to collect carbon dioxide. So, but it's not just carbon dioxide. We also have some water vapor in there. The water would take up a little volume, but we ignore it. We ignore it. So of course the presence of water, yeah, it's going to impact the volume slightly, not the temperature, but the pressure. So it's not only the carbon dioxide, but it's also the water that the collisions are pushing down and then causing the water to be pushed out, be displaced. Well, scientists have determined that the amount of water vapor present is all based on the temperature. Room temperature, roughly 25. At 25 Celsius, 23.8 millimeters of mercury. Remember, the atmosphere at sea level, fair weather, is approximately 760 millimeters of mercury. So it's not much, but we have to account for it. Right? So can we pause here and then go in our packet to the multiple choice questions that we spent our first period together yesterday answering? And can you find number 15? All right. Can you read, dig in, think about it? Yeah. Also employing Dalton's law of partial pressure. Michael, yes, no. Please remember. Okay, so to pick up exactly where we left off yesterday, if we return to, oh, sugar, mine are not numbered, I'm so sorry, but it's ideal gas. Okay, as we're finding our way there, what concerns can I address? Anything that you're questioning, not quite fully confident on? Going through the list? Okay. No, that was an indication of something. Sorry. Oh, was she congratulating you? Yeah. Is that a struggle? Yeah. Which I take responsibility because no, something else. These copiers. I do, and I put it. It just does it to frustrate you and me. So sorry. I take full responsibility. Yeah, we always have those ones that. No, just kidding. We do, don't we? Like you always have like that one student near you that like never on the page that we're on. And they reveal themselves because they like, look, Michael, I hope you're not that person. Grace, I'm not saying you're that person. We don't have any of those people in here. People, you're that person in other classes. All right. So we reminded ourselves that molar mass, gram per mole, so we could actually have an equation for it. And of course, density, mass per unit volume. All right. The ideal gas law is the gift that keeps on giving. Absolutely. On the surface, it seems that all this will reveal for us is the pressure if we know all the other variables, or the temperature if we know all the other variables. Now, where the other gas laws take us between scenarios. Yeah, we have a gas at constant temperature, constant amount. That's why we can only look at the relationship of pressure and volume. So we're saying, okay, we have this gas at this pressure and this volume. Well, what if we change the volume? How will the pressure be? So we're changing, but not here. This is you have a sample of gas. If you know temperature, amount, volume, you can find pressure. Okay, there's so much more that this can give us. All right, Sir Bryce, can you rearrange this expression for moles? I'm sorry to insult your intelligence. I'm sorry? Yeah, so what? N equals, you got it. Remember, I'm always going to use capital MM for molar mass. Zumdahl just uses a capital M. Well, we just have another expression for N. Can't we substitute that in? Absolutely. So we have PV equals M over MM RT. Oh. And now this opens up. Not that you couldn't develop the problem solving just from this, but you probably have to do a couple steps. God bless you. But if we look at, well, how can we use this? So we said molar mass. Well, look, we could derive molar mass just right from this equation. So you could get molar mass, I know, MRT over PV. Yeah. Oh my, mass divided by volume is density. So we could get pressure if we divide by RT times molar mass equals mass divided by volume or density. Sorry, I'm just putting brackets around that just so we know that's one combined, MM. Couldn't we also say molar mass is equal to density RT over P? Yeah. I could rewrite mass divided by volume as density. The problem we looked at yesterday, they asked us for the mass of oxygen. Remember, we solved first for N, and then we converted to grams. Well, we could just do it all at once. I will give us the ideal gas law because board gives you the ideal gas law. We have to know how we can derive these. If you just start from there, and molar mass is gram per mole, and just do the rearranging. All right, Colton, sir. Can we just do one of these? So could you please choose for us 1, 2, no. I'm so sorry. Oh. 4 or 5. Sure. Okay, so can I turn it over to you? I'm going to problem solve at the same simultaneously, and then we'll make sure that we all get that 13.7 grams per mole. Concerns? Yes, ma'am. Oh my gosh. Golly. Thank you. Thank you. I went too quick. I counted for it in the calculation. Forgive me. Thank you very, very much. Okay, the R value is 0.08206 liter atmosphere. So it's just liter in atmosphere in our numerator per Kelvin mole. Often, if it's a college board question, we'll often see, instead of writing in the denominator, they'll express these to the -1. So that's just another way we could see it. Yeah. Sorry. That isn't equal to that, but did that address what you need? And you're given that. You never have to memorize that. Yeah. And all those units, I can't help but just encourage, well, we have to write them, right, with our number. You don't have to ever do canceling, but that helps me ensure I've set up the problem correctly. And then we get gram per mole. Any other clarity needed? Okay, Dylan, I know you've been so excited for this, so we're finally there. We're finally there. So if we turn our page, oh! So we've done stoichiometry with gases in chapter 3, but we never dealt with their volume. We only ever calculated their moles or their grams. Now we have the knowledge we need to do true gas stoichiometry. All right, no molar volume. We are permitted to use molar volume only at STP, 22.414 liter per mole. I remind you of that because we know how critical moles are to stoichiometry. All right. Let's dig into this first. Please read. Mackenzie, would you mind sharing what you come up with for the balanced equation? Oh, whenever you're ready. Excellent. How did you know that sulfur was a solid? In every way, shape, or form, you are correct. We could use some terminology within the problem to help us. So how do we usually talk about quantities of gases? Liters. Liquids, solutions, milliliter or liter. Solids, grams. Yeah? Don't talk about the volume of a solid. We're never looking for that. So because it's asking for mass, but of the nonmetals, only nitrogen, oxygen, fluorine, chlorine, and then the noble gases are gases at room temperature and pressure. Sulfur is a pale yellow solid. Wonderful, wonderful, wonderful. All right, what mass of sulfur when added to oxygen will produce? 12.611 liters. Okay, and Damien, when you see at STP, what do you immediately think of? You get clearance. You can use it whenever you need it. So let's see. Whatever we're given when we're doing stoichiometry, how do we know we need stoichiometry? because you're starting in terms of one thing and asked about something else within the reaction. Do you understand that we needed the reaction first? Because you're going to pull from it your mole ratio. Okay, so our goal, whatever we're given, is to get to moles. Volume, nice. A unique case, molar volume is experimentally derived. We report it with 5 sig figs because hardly ever are we limited to beyond 5 sig figs. So the potential that this can limit your sig figs is absolutely there. 5, 4. Here, as I know that we want to try to avoid our average atomic masses or molar masses limiting our sig figs, we're okay here. As long as we're consistently reporting to the 100th place, totally fine. So 1804 grams of sulfur. Okay. I know, Dylan, you're saying, oh, too easy. So just crank it up a notch. Okay, Dylan, you choose. Do we want to do the next problem or the bottom problem? All right. Nice. Given the balanced equation, Michael, could you help with phase symbols, please? Not that they're necessary, but I just want to put them. Wonderful. Absolutely fantastic. Absolutely fantastic. All right. How many liters of carbon monoxide? Oh, an STP. Can be produced from the burning of 65.5 grams of carbon. I'm starting in terms of the carbon and calculating to the carbon monoxide. I'm given grams of carbon, and I always want to get to moles as soon as I can. And I know we can go from grams to moles. Next step, mole ratio. Here's where you make a choice. We're in terms of our gas. How do we get volume? You could pretend that we're at STP for a moment. You could. So here's like where the road splits. If we want to just pretend for a moment we're at STP, then we can use 22.414. Get what the volume will be at STP. But we're not at STP conditions. We're at these. So whatever this is, and 22 liters. Okay, that is the volume when the temperature is 273.15 Kelvin and the pressure, since this is given in millimeters of mercury, is it okay? I'm going to reference what standard pressure is in millimeters of mercury. When you pull the conditions of STP from your memory, they should never limit your sig figs. Never limit. That comes from our memory. Then, if we want to call these V1, T1, P1, and this would be T2, and this would be P2, we'd have to solve for V2. The other path, the ideal gas law, deserves its name. Ideal, we should say the wonderful, dependable ideal gas law. Because the ideal gas law could care less if we're at STP or not at STP. The ideal gas law, whenever we need it, we can just call on it. So I know in first year chem, sometimes I'll refer to this as the fairy godmother equation. So the fairy godmother, whenever you're in a sticky situation, you just call on her and she flies in. And with her magic wand, she makes everything better. Well, not everything, but the situation less sticky. The magic wand of the ideal gas law is R. The gas law constant, that's what kind of accommodates if we are or are not at STP. It just makes everything okay. So here, I have moles of my gas, but I'm not at STP. Ooh, here comes the fairy godmother. So I know the pressure I'm at. I know the temperature. I'm looking for the volume. So I stop at moles of gas. And this is 5.45 moles of carbon monoxide. And then PV equals nRT, solve for volume. You will be given your pressure relationships to do the conversion. So we don't have to remember 760 is 1 atmosphere. You'll be provided that. And we get 543 liters of CO. You would get the same thing. I think if we go this route with molar volume, we get 542, if I'm not mistaken. Yeah, thank you. And you will have shown your work. And so I know that we could differ because we're adjusting for sig figs, adjusting for sig figs. That explains the difference. So you make the decision, but we need to know like when. So as we're solving these, I think sometimes a strict problem, you're just so good at them, kind of just get them done. But we need to make sure we understand like what perspective we're in. That's why I take a moment to put phase symbols, but not required of you. I want to make sure that I'm not missing. Okay, where do I need to pause? Okay, Dylan, we are going to answer what you're thinking. Okay, Mrs. Gearhart. Well, we know we're not always given mass and ask for volume. What if we're given volume and ask for mass? Well, here you go, sir. Can we get our equation? And I'm so sorry, I wrote on my screen. element plus compound, sigma replacement. Are you guys good on the? Yes. Absolutely. Absolutely. Okay, so if we're going to use and put ourselves as if we were at STP, we're going to apply molar volume, and then you get 122 liters of carbon monoxide at STP. Rishi, do you want to call this V1 or V2? Sure. So if we are calling this V1, then our T1 is 0 Celsius or 273.15. And then our P1 is 1 ATM or 760 millimeters of mercury. I'm going to favor millimeters of mercury because the pressure you're actually at is millimeters of mercury. All right. P1 V1 over T1 equals P2 V2 over T2. I like to rearrange my equation first. You, of course, don't have to. You could rearrange it, but then not show me the work. Totally fine. Is that okay? Could someone please share what is the balance equation? You guys are superstars, absolutely superstars. But I need to check in with you about this. So you're reacting sodium with water. What do we get? Unless I told us, that's what I would expect us to get. So Isaac, thank you. Because sodium and hydrogen both are going to be cations. This is acting as a cation, so that's absolutely. But there's an exception. So I would never have this on a task for us unless we talked about it or I gave you a little hint. Sodium, being an alkali metal, is one of our most reactive metals. Alkali and alkaline earth metals react with water differently than the transition metals if they're reactive enough to replace hydrogen. We're definitely going to get hydrogen. What other product could we get? Isn't that what Isaac said? Yeah. So, yeah, Isaac said Na2O. That would be perfect if it wasn't an alkali metal, or an alkaline. Go ahead, Maddie. Sodium hydroxide. The more reactive metals produce the metal hydroxide, not metal oxide. Isaac, thank you very much. Maddie? Twix, M&Ms. Very good, very good, very good. You're welcome, you're welcome. Okay, so does that change your mole ratio? I will confess, I love the ideal gas law. That is what I choose, but you don't have to choose. Absolutely. So from the get-go, we need to make an adjustment. When you're starting with volume, how do we get that to moles? Well, you could use 22.414 right off the bat. Oh, wait. I'm so sorry. I need to address this. And that, if you're choosing the route of molar volume, Rishi, is that what you like? Totally fine. Totally fine. Can we do this? This is at STP. Is this at STP? No. So what we need to do, if you want to use molar volume, is correct that to be at STP using the combined gas law. So when you're given volume first, if you like molar volume route, you need to adjust it to be at STP. Then you can use 22.414. What I chose to do is first, ideal gas law, find the moles. Again, that's what we need to continue our stoich. So just solving for n and then continuing with the stoich. So go either way. We'll practice more. Questions? Tomorrow lab, please have the, pre-lab heading, objective, procedure, data tables ready. And I gave you some good guidance. If anyone needs an extra one of these, go ahead and grab it.